day everyone, my name is Harun and I'll be taking you through organic chemistry. So I don't think most of you are new to organic chemistry because some way or the other you must have heard of it, and even if not, you always deal with organic compounds on a daily basis. I mean, as much as you add sugar to your tea and unknowingly you deal with organic compounds virtually every day. So what is organic chemistry? Actually, organic chemistry is just simply the study of carbons. So we say it is the study of carbons and its compound. It's the study of carbon and its compounds. That is what organic chemistry is all about. However, if you critically look at this, you will find out that there are still some carbon compounds that are inorganic. I mean, that cannot be gotten from natural source, because the term organic actually means things that are free from artificial production, things that are only gotten from natural source. I mean, from plants and animals. But if you critically look at it, organic chemistry is the study of carbon compounds. We still have some carbon compounds that are actually not gotten from natural sources. Examples are carbonates. So if you have something like calcium carbonate, of course this is limestone, of course this is gotten from probably from natural source as well, but most of limestone are now produced artificially, and so many other compounds. So this is basically an inorganic compound. So we say carbonates, triazocarbonates, maybe calcium carbonate, potassium carbonates, and other triazocarbonates, and metallic carbides, so carbide ions, maybe like calcium carbide, aluminum carbide, and other metallic carbide, as well as the oxides of carbon, like CO2, CO. All these are exceptions to the definition of organic chemistry. So it means that if you critically look at it, we'll now define organic chemistry as a branch of chemistry that deals with the study of the physical and chemical behaviors of carbon compounds, except triazocarbonates, metallic carbides, and oxides of carbon. So these three categories are exception because they contain carbon, yet they are inorganic compounds. So having gotten the full knowledge of organic chemistry, you'll be wondering, why do we have to study why do we have to devote a whole branch of chemistry to the study of carbon only, out of all the elements in the periodic table? Why carbon? And why is it even called organic in the first place? So actually, when the compounds that contain carbon begin to emerge, like alcohol and other compounds, they usually are gotten from natural sources. They usually are gotten from plant or animal sources, and they cannot be synthesized in the laboratory until in 1828, when Frederick Wohler. So this year, a man called Frederick Wohler is an organic chemist, a German chemist. He was the first person to synthesize an organic compound in the laboratory artificially. So if you're asked, what is the first artificial organic compound that was synthesized? It was actually urea. So this was done in 1828. And after then, so many organic compounds are now synthesized in several ways in the laboratory. So, but because the name organic was initially coined due to the fact that these substances are gotten from the original source. So even today we know that there is no any organic compound that we cannot synthesize artificially, but the name has remained. So the name organic is hence coined. So why do we have to study carbon separately out of all the elements in the periodic table? This is practically because the carbon compounds are very much more than the compounds of all other elements combined together. So I am saying that all the compounds that we have in the whole world, just think of it. It could be NH2, it could be NH3 ammonia, it could be calcium carbonate, it could be water H2, it could be silicon oxide, which is present in sand. It could be any compounds that you can think of. All these compounds combined together, they are nothing compared to the compound of carbon. They are nothing compared to the carbon containing compounds. So we say that the carbon containing compounds are too much and they excessively dominate all other compounds in chemistry combined together. So because of this complexity or the ability of carbon to form so many compounds, that is why it has been divided in such a way that organic chemistry, or a chemistry dealing with the study of carbon, has been gotten, and this is a unique division of branch of chemistry on its own. So now, what is responsible for this unique ability of carbon? There are actually three things that are responsible for this unique ability of carbon. One of them is the ability of carbon to catenate. So number one, we have catenation. And the second is due to the presence, is due to the fact that the electronic configuration of carbon is kind of special. I'm going to explain that. So it is due to the electronic configuration of carbon. And as well, due to isomerism. So these three scenarios are what accounts for this special ability of carbon. And I'd like to take it one by one so that you can get a full understanding of this. So, catenation. Catenation is simply the ability of elements to form continuous chain. So they keep adding to it successively. So why is carbon special? Now, not only carbon have the ability to catenate, even sulfur do catenate. But carbon is special because when it catenates, even all the successive members resulting from this catenation are very, very stable compared to another element like sulfur. Sulfur as well can catenate. So what I mean by catenation is simply like carbon can form a bond with carbon, which can form a bond with another carbon, and another carbon, and another carbon, and so on. This is catenation. And you can agree with me that at each successive formation of bond with carbon, we are generating an entirely new compound. So when we have a single carbon-carbon bond, this is a compound. When we have another carbon attached to it, this is an entirely new compound, and so on. So all these chains, this is just like 6 carbon chains. We can have it up to 20, 100, 1000, and so on and so forth. It does not have any. So due to the fact that carbon can catenate, it also have the ability to maintain its stability despite this very long chain. So carbon-carbon chain is stable, but if you have carbon-carbon chain times 50, it is also very, very stable. However, other elements that can catenate cannot maintain this stability. For instance, when sulfur catenates, it fails to remain stable. It fails to retain the full property of an initial sulfur or sulfide ion. So this is why carbon is unique in respect to catenation. So catenation, or the ability of carbon to form continuous stable chain, is regarded as catenation. And because of this, carbon is able to generate a lot of compounds. Another thing is the electronic configuration of carbon. Carbon in the periodic table is number 6, therefore it has an atomic number of 6. And if you draw the electronic configuration, you'll find out that there is absence of lone pair of electron. So carbon is 6, which is 1s squared, 2s squared, 2p squared. So if you have to draw the electronic shell of carbon, you're basically going to have 2 shells, the s and the p shell. So the s shell contains just 2 electrons, and you are left with 4. And the remaining 4 electrons are actually dispersed around the p shell. So you can see that the outermost shell contains only single electrons. You have 1 electron here, 1 here, 1 here, 1 here. And there is no lone pair of electrons. Lone pair of electrons means the electrons are already bonded together. Let's say something like this. This is a lone pair of electrons. So due to this absence of lone pair of electron in the outer shell of carbon, it maximizes its ability to form bonds. Because carbon is one of the few compounds that have the ability to form 4 bonds, that have the ability to retain what is called tetravalence. Unlike any other compound that you can pick randomly, let's say nitrogen, after carbon of course, let's say we have nitrogen. So nitrogen is actually an element that comes after carbon. So nitrogen of course, atomic number is 7, and if you draw it, the outermost shell is going to contain 5 electrons, which is 1, 2, 3, 4, 5. Now there is a presence of a lone pair of electron in the outermost shell of nitrogen atom. Because of that, when nitrogen is forming bond with hydrogen, we only have something like this. And this is what ammonia, NH3. So it means that the maximum number of bonds that nitrogen can form is 1, 2, 3. However, the maximum number of bonds that any element can form at once is 4, and carbon exhibits that. And that is a phenomenon known as tetravalence. Another thing that accounts for this unique property of carbon is isomerism. And isomerism actually originates from its ability to form continuous long chains. So when these long chains rearrange, we form an entirely new compound, and that is what isomerism is all about. So let us look at these 6 carbon chains. Okay, so these 6 carbon chains, we could rearrange it as 1, 2, 3, 4, 5. Let's say, okay. So let's just say 1, 2, 3, 4, 5, and let's just put the 6th one there. Okay, we still have 6 carbon chains, but in the sense these are entirely different compounds. For instance, if I'm to name this compound, this is a hexane. This is hexane, 6 carbon chain, an alkane. But however, this particular one is 3-methyl hexane. That is, one of the carbon at the end has been moved and it is placed as carbon 3. So you can see this is an entirely different compound. And how do we generate the compound? By simply rearranging an initial compound, right? So it means that if you go on rearranging this particular compound, we are going to generate a lot of compound from one compound still having the same number of carbon, and that is isomerism. So these 3 properties are actually the things that account for the uniqueness of carbon. Having understood this, we'll now quickly look at the classification of organic chemistry. So how do we classify organic chemistry? So organic chemistry, generally, we broadly classify it into hydrocarbons and non-hydrocarbons. So we say the organic chemistry is broadly classified into we have hydrocarbons and we have the non-hydrocarbons. So the hydrocarbons, from the name hydrocarbons, it means they are elements that contain, or they are compounds rather, that contain carbon and hydrogen only. We already said organic chemistry is a study of carbon and its compounds. So when we see a carbon compound that contains only 2 elements, or we call them bimolecular compounds because they contain only 2 elements, they are usually carbon and hydrogen, and these are called hydrocarbons. So hydrocarbons are organic compounds that contain carbon and hydrogen only. However, the non-hydrocarbons, in addition to containing carbon and hydrogen, they could also contain an additional element, for instance, nitrogen, sulfur, and any other element. All this kind of, yet they are organic compounds. So these kind of organic compounds are not regarded as hydrocarbons. They are organic compounds, but they are what? Non-hydrocarbons, because they do not contain carbon and hydrogen only. They contain some other elements in addition to carbon. For instance, the first example I gave was urea. Urea, in addition to containing carbon and hydrogen, it also contains nitrogen. So because of this, it is what? Non-hydrocarbon. Now, both the hydrocarbons and the non-hydrocarbons could be saturated or unsaturated. But before I give you these examples, let me just quickly illustrate what I'm saying. So if you have something like this, so this is called ethane. This ethane molecule, you can all agree with me, obviously, it contains only carbon and not hydrogen only. So you can always write this as C2H6. So this is ethane. We can see it contains 2 atoms of carbon and 6 atoms of hydrogen. So this is of course a hydrocarbon. However, if I just clean this hydrogen here and I add OH there, this is an entirely new compound, and this is an ethanol. So if you want to write this is C2H5OH. Now because of the presence of another element that is different from carbon and hydrogen, which is what? Oxygen. Because of the presence of oxygen in this compound, this is an alcohol. So because of the presence of oxygen here, this is a non-hydrocarbon. However, this contains only carbon and hydrogen, therefore it is a hydrocarbon. So I do hope you get the clear difference between hydrocarbon and non-hydrocarbons. Now the hydrocarbons, as well as the non-hydrocarbons, could be saturated and they could also be unsaturated. So both of them could be saturated or they could be unsaturated. So saturated or unsaturated. And this as well could be saturated or unsaturated. So, what is saturation and what is unsaturation? Of course, we are also going to discuss that. But let's just go on with our classification. Now, the hydrocarbons, which are carbon-containing compounds or compounds that contain carbon and hydrogen only, they could also be further broken down into 2. Okay, so we have could have aliphatic. We could have aliphatic hydrocarbons as well as we could have aromatic hydrocarbons. Okay, and the aliphatic hydrocarbons would also be acyclic and cyclic or alicyclic. Okay, now let me take it one by one. Okay, so the hydrocarbons are divided into aliphatic and aromatic hydrocarbons. So the aliphatic hydrocarbons are just straight chain hydrocarbons, like the ones that I have been giving you. They are just chained hydrocarbons, like the ones that I've been giving you, like you could see carbon forming and all that. The acyclic hydrocarbons are just chained hydrocarbons, which are aliphatic hydrocarbons are just chained hydrocarbons, which are like this. However, these chain hydrocarbons could rearrange themselves to form a kind of cycle. So when they are just simple chain hydrocarbons like this, they are called acyclic. That is, they are not circular. However, they could also rearrange themselves to form cycle. For instance, we have something like this: 1, 2, 3, 4, 5. These are 5 carbon chains. Now, these 5 carbon chains can decide to rearrange themselves as something like this. Okay, as something like this. So if you count the number of carbon here like this, 1, 2, 3, 4, 5, and it is the same as number of carbon here, 1, 2, 3, 4, 5. However, this is an alicyclic hydrocarbon because the carbon do not arrange themselves in a cyclic ring. And in this place, still the same number of carbons, 5 carbons, they arrange themselves in a cyclic ring. So this is an alicyclic hydrocarbon and this is a cyclic hydrocarbon, and both of them are aliphatic hydrocarbon. Okay, so and hydrocarbons that can exhibit this could actually be of 3 forms. It could be of alkanes, it could be alkenes, and it could be alkynes. And all these we are going to look into them in details. Then as for the aromatic hydrocarbons, these are just benzene and benzene related hydrocarbons, or benzene and benzene related hydrocarbons. So when we say benzene, benzene is also a ring hydrocarbon, but it is different from other normal cyclic hydrocarbons. Okay, so for benzene, it contains double bonds. So we have something like this. Now, if I ordinarily draw something like this, you observe before I go there, for this cyclic hydrocarbon, which is 5 carbon chains, I could just decide to draw it as a pentagon like this. So this is actually the same thing as this. It means that each of these joints here are actually representing what? They are actually representing that there is a carbon atom there. So each of these joints represents carbon atom, and same thing is applied to here. So ordinarily, if I draw a ring like this, and let me just chip in something on nomenclature. So because this has 5 chains and it's an alkane, I'll say it is pentane. But this also has 5 carbon chains, but it's in cyclic form. I'll say it is cyclopentane. I'll add cyclic to show that it's what? Cyclic aliphatic hydrocarbon. Now, ordinarily, if I have something like this, having known that each of the joints represents carbon, so you could count that we have 1, 2, 3, 4, 5, 6. We have 6 carbon in this compound present in a ring structure. So from your polygons, you know 6 shapes are called hexagon. So this is a hexane, but because it's in a cyclic form, we say it is what? Cyclohexane. However, when it comes to aromatic hydrocarbon, they are not just normal cyclic compounds. You have something like this with a resonating double bond around it. So you have a double bond here, here, and here. So this is called benzene. This is called benzene. Now this benzene has a special ability to undergo resonance, and these double bonds can actually rotate and keep rotating, and that is what leads to the resonance of benzene. So we could actually still have it as something like this. The double bond must not proceed each other. They not to have more than 4 bonds around the carbon atom. So we can also have something like it could also rotate, like this double bond rotates. So it could also be something like this. So it could also be something like this. So in summary, August Kekul, which was the person that proposed the ring structure of benzene, actually said that instead of drawing benzene in any of these alternate structure, you could also just draw the Kekul structure of benzene, which is just having your benzene and putting a ring inside this. So all these 3, any of them you draw, are still what? Benzene. Note, they are different from cyclohexane, which I had explained earlier. So the benzene have 3 double bonds there, which can actually always rotate. So So because of the ability of the double bond to continuously rotate, just like the three fans of your fan. So because of the ability to continuously rotate, you begin to see the fan as though it is just a cycle. So and that is why August Kekul proposed this structure called the Kekul structure of benzene. So if you just see something like this, of course it is benzene. So the aromatic hydrocarbons are just benzene and other benzene-related compounds. So other benzene-related compounds are also aromatic hydrocarbons, but however, most of them are non-hydrocarbons. Okay, so which means that in addition to carbon and hydrogen, they contain other elements. For instance, when you attach OH to benzene, this is benzene, and we already attach OH to it, you can say it is hydroxybenzene, and this hydroxybenzene is otherwise called phenol. It's otherwise called phenol. Okay, we could also draw a benzene and attach, let's say, NH2 there. Okay, let's say NH3 there. This is aminobenzene, and this aminobenzene is otherwise called aniline, which is used in the production of dye. So we have many other benzene-related compounds. If you have CH3 to it, that is methylbenzene, which is toluene, and we have 2CH3, we could have xylene. All these are benzene-related compounds. That is, we have benzene as a main compound and some other compounds attached to it. However, I want you to get it clear that benzene itself is a hydrocarbon, that is, it contains only carbon and hydrogen. However, most of other compounds of benzene, other benzene-related compounds, are non-hydrocarbon because they contain an element that is in addition to carbon and hydrogen. For instance, phenol now, we all know that each of these joints or each of these point angles represent carbon. But in addition to this carbon here, we have oxygen and hydrogen. So because of this oxygen, this is a non-hydrocarbon. As well as your aniline, because of this nitrogen here, this is a non-hydrocarbon. Yes, they are aromatic compounds and they are benzene-related compounds. So, having gotten a clear picture of aliphatic hydrocarbons, the acyclic and cyclic and the aromatic as well, now we will now explain what it means for an organic compound, be it hydrocarbons or non-hydrocarbons, to be saturated or not saturated. So when is a hydrocarbon said to be saturated? A hydrocarbon is said to be saturated when the carbon element use all its 4 valence electron in forming bond. We've seen that carbon is tetravalent. So when it uses all these 4 electrons around the shell, when it uses all these 4 electrons in forming bonds, then the carbon element is what? It is said to be saturated. That is, it can no longer form any bond except by substitution reaction. So we have a carbon like this. It is tetravalent in the sense that it has 4 valence electrons. So we have 4 electrons around, right? So when it uses all these 4 electrons in forming bond, let's say it's formed bond with hydrogen here, it forms a bond with hydrogen here, a bond with hydrogen here, and a bond with hydrogen here. Now it has already exceeded the limit. It cannot form any more bond again because it is tetravalent and it has already used all the 4 valence electrons in forming bond. This is a saturated hydrocarbon. I want you to look at it as like you are studying, and you know that for you personally, you cannot study more than 5 hours. I know that after 5 hours, you cannot study again. There is no how. If you read, you will not understand. So it means that that 5 hours is your saturation point. That's your limit. So once it is, you read from 12 to 5, that is 5 hours. So you know any other thing you are reading, you are just deceiving yourself. It means you've already gotten to your saturation point. That is exactly how you have to imagine this carbon now. It has only ability to form 4 bonds. So once it has already formed 4 bonds, it is saturated. It can't go beyond that. So that is the meaning of a saturated compound. However, an unsaturated compound did not use all the valence electrons in forming bond, and because of that, it can still undergo further chemical bonding. So which means that you can read for 5 hours and you have only read for 3 hours, which means you still have the ability to undergo more reading sessions. So that is the meaning of you are still yet to be saturated, so you are still unsaturated. So that is the meaning of unsaturated compound. Let us look at a 2 carbon compounds. Like this is carbon, carbon. So originally, if we have this is saturated, right? Because you can see this carbon we have 1, 2, 3, 4. And for this carbon we have 1, 2, 3, 4, right? So let me just say I have hydrogen. So everything is hydrogen. So this is a saturated compound. This carbon forms 3 bonds with hydrogen and 1 bond with carbon. While this carbon forms 3 bonds with hydrogen and 1 bond with the other carbon. That is 4, 4, right? Now, if this hydrogen here and this hydrogen here, I eliminate them, what happens? It means that there is a deficiency of, there is the presence of an electron here and the parent of an electron here, which is still able to undergo bonding, right? So this electron actually join together to form this. That is, we have a parent of an electron here, a parent of an electron here that is empty, and they can actually still accommodate more compounds to form bonds. So this actually like combine together to form an extra bond here. So this is an unsaturated hydrocarbon. So this hydrocarbon is unsaturated, and if you want to react it with something like HCl, it can just break this bond and form hydrogen there and Cl there. But if you want to react this with HCl, for instance, you cannot react it, you can only substitute. So you can only bring in chlorine and remove hydrogen. That's substitution reaction. And that is when the compound is said to be saturated and unsaturated. For my explanation, we will conclude that the saturated hydrocarbons are usually single bond, and the unsaturated hydrocarbons are multiple bond. So among these aliphatic hydrocarbons that I've mentioned here, alkanes are usually single bonds, alkenes are double bonds, and alkynes are what? Multiple bonds. So this means that among all these, only alkane is saturated, alkane is unsaturated, and alkyne are what? Very more unsaturated. Let us also look at benzene. Benzene has a double bond here, a double bond here, a double bond here. So it has 3 double bonds. It means that benzene is what? Highly unsaturated, because we have a double bond here, which means we have about 6 bonds. We have 3 double bonds. So that is the meaning of when the compound is said to be saturated and unsaturated. We'll explain aliphatic, cyclic, and all that. So for the cyclic hydrocarbons, let me just say something before I round off. For the cyclic hydrocarbons, we could have the cyclic hydrocarbon to be homocyclic. It could also be heterocyclic. Okay. For instance, if we have something like this is a cyclic hydrocarbon, right? You know, this is a cyclic hydrocarbon. It's not benzene. It's not containing double bond in 3 places, so it's not benzene. This is a what? Cyclic hexane. So this cyclic hydrocarbon now is just a homocyclic hydrocarbon because it only contains hydrogen, and all these joints are carbon, 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 and each of these carbon contains hydrogen, hydrogen. All these bonds are just what? Hydrogen. So it only contains carbon and hydrogen, so it is homocyclic. However, the heterocyclic contains a third element, okay, apart from the hydrocarbon. So it's a non-hydrocarbon, which means most non-hydrocarbons are what? Heterocyclic. Most cyclic non-hydrocarbons are heterocyclic. So if I have something like this, and then I have OOH, or let me just put OH, okay? So this is a cyclic alcohol. In this case, this is a what? Heterocyclic compound. Because of the presence of what? The O, so making it what? Heterocyclic. And also the cyclic compounds will be saturated and unsaturated. Of course, this particular one is saturated because there is no multiple bond there, so we don't have double bond or triple bond. However, if I just add a single double bond here, it becomes what? Unsaturated. So you use the presence of double bond, triple bond to indicate that the compound is unsaturated. Then, this is all I will be leaving you with for the introduction to organic chemistry. In our subsequent class, we'll be continuing. But I would just like to leave you guys with only one question that would actually boost high understanding of the topic. So the question is actually talking about which of the following is in line with the description given. So we have a description and you are expected to select a compound. So the question is, which of the following conforms with the characteristics? We have 3 options. I would like to give you the options first. So we have oxylene. Option B is, we have benzene, aniline, nitrite. Benzene. Option C is aniline. And option D is nitrite. Now listen to the question. The question is, which of the following conforms with the characteristics? And what are the characteristics? They say the compound is highly unsaturated, heterocyclic, non-hydrocarbon. Highly unsaturated, heterocyclic, non-hydrocarbon. So this is the description, and they say which of the following conforms with it. I would like you to attend this. But of course, I'll just give you a clue. You see, oxyrene, you might have not heard of it before. Oxyrene is just oxacyclopropane. So it's just something like this. Oxygen here, CH3. So this is oxyrene. And for the benzene, of course, you know benzene. This is benzene here. As for the aniline, I think I've told you about aniline. This is aniline here. Adding ammonia to what? Benzene. And as for the nitrite, nitrite is just R triple bond N. That is a methyl group forms a triple bond with what? N. So we could have something like CH3 triple bond N. So all these are the compounds. Now, which one is highly unsaturated, heterocyclic, and is a non-hydrocarbon? If we look at all these examples now, firstly, oxirane. Oxirane is what? Saturated. It is not unsaturated, so it can't be oxirane because the first condition says it must be highly unsaturated, right? If you look at benzene, benzene is unsaturated. If you look at aniline, aniline is a benzene, so it's also unsaturated. And if you look at nitrite, nitrite is also unsaturated, so this one has to go in. Then it must be heterocyclic, which means it must be a cyclic compound with an additional element apart from the carbon and hydrogen. So if you look at benzene, benzene is homocyclic because this is benzene, it only contains carbon and hydrogen. So it can be benzene now in this case. Now if you look at aniline, in addition to being cyclic, it has what? Nitrogen. So which means it is what? Heterocyclic. And then if you look at nitrite, nitrite is not even a cyclic, it is a straight chain hydrocarbon. So it can be nitrite. So it means we are only left with one answer, which is what? Aniline. And the last condition is what? Non-hydrocarbon. And of course, aniline, because it contains nitrogen, it's what? Non-hydrocarbon. So which of the following conforms to the description? Highly unsaturated, heterocyclic, non-hydrocarbon. The right answer would be what? Aniline. So I would like you to practice more questions and to foster your understanding. And if you have any question, please drop your questions in the comment box and like the video and subscribe to the channel for more updates. Thank you very much for your time.